5. This tutorial will be about the algorithm of gradient descent. Given a function f from Rn to R, a continuously differentiable and convex, we would like to find its global minimum. We would use an iterative algorithm. We will start at a given point, x0, and we would take a step in the opposite direction to the gradient at any given point. Using a step size alpha, we would stop when reaching a stopping criteria. Let f of x be the following function, with q positive, definite, and symmetric. So, assuming the step size is constant, let's find an upper and lower bounds on alpha for which the gradient descent algorithm will converge to the true solution. I encourage you to pause the video right now and use these hints to try to solve the question yourselves. The optimality condition is that minus the gradient, and the gradient itself is 0, meaning that b is equal to qx star, and the gradient is b minus qx. And so, by the definition of gradient descent, xk plus 1 is equal to xk minus alpha of the gradient, which is equal to xk plus alpha b minus qxk. But each of these xk's has been defined as well by the definition of gradient descent as xk minus 1 minus alpha and the gradient of f at the point xk minus 1. And so we can group xk in this side and to get this expression, and by opening xk minus 1 and then xk minus 2 and so on, we would get this expression, I minus alpha q raised to the power of k plus 1 x0, plus alpha sum I minus alpha q raised to the power of j b. Well, j is the iterator that goes from 0 to k. Let's define a to be I minus alpha q, and so we would have the simple expression xk plus 1 is equal to a raised to the power of k plus 1 x0 plus alpha, the sum from 0 to k, a raised to the power of j q x. And so, in order to ensure that the algorithm will converge, we must demand that the spectral value of a is in absolute value smaller than 1. As you have studied in numerical algorithms, when an iterative method is taken, we need that the spectral value of the iterating matrix would be smaller than 1. And so we want that for every I, lambda I of a is smaller than 1. That is meaning that the absolute value of 1 minus alpha lambda I of q is smaller than 1. This is how we derive this expression. And then what does that mean for us? That we need that minus alpha lambda I of q to be smaller than 0, that meaning that alpha has to be larger than 0 itself, and alpha lambda I of q has to be smaller than 2. That is meaning that alpha is smaller than 2 divided by lambda I of q for every lambda I. That is meaning that alpha is smaller than 2 divided by lambda max of q, because that is true for every I. And so alpha needs to be between 0 and 2 divided by lambda max of q. We define the convergence ratio to be as follows. Let's find the optimal step size alpha, which would lead to the smallest convergence ratio. We can see that the convergence ratio is defined to be the distance from the optimal solution at r iteration divided by the same distance at the previous iteration. Viewing the solution, I suggest you try to solve it yourselves and then view the solution in this video. So we will divide the solution to parts. The first part, let's find an expression to xk plus 1 minus x star. So this expression could be derived as I minus alpha q xk, as we have seen in the previous question, plus alpha b, and that is equal to I minus alpha q xk plus alpha q x star, because we know that qx star is equal to b. That is meaning that xk plus 1 minus x star is equal to I minus alpha q xk minus. So let's bind the result expression from above. Let's use the inequality so the norm of ax is smaller than the norm of L, a, multiplied by the norm of x. And so the norm of xk plus 1 minus x star is equal to this expression by the previous slide. That is equal to the norm of I minus alpha q multiplied by the norm of xk minus x star. If we divide this expression by the norm of xk minus x star, we would get that beta being xk plus 1 minus x star divided by xk minus x star is smaller or equal than the norm of I minus alpha q. And that is equal to the max over the absolute value of all of the eigenvalues of this function, which are 1 minus alpha the lambda i's of q. This is as you have seen in the previous courses. That uses the norm of a being the maximum over I of the absolute value of lambda I of a. So let's denote lambda I as lambda I of q for it to be more comfortable. So the optimal step size can be found by minimizing the upper bound on b that we have found in previous slides. And so alpha optimum is the minimum over alpha of the maximum over I of the absolute value of 1 minus alpha. The solution to this minimization problem can be found graphically. So in this graph, we have the alpha axis on the bottom and the absolute value of 1 minus alpha lambda I axis on the top. We know that the steepest descent will be for lambda max, and it will be 0 at 1 divided by lambda max, and then it will rise up again. And the mildest descent will be with lambda min. And so the minimal point of maximum over I of the absolute value of 1 minus alpha lambda I has to be above all of these and also above all of these. So it has to be in this region, and it will be in the point when this graph and this graph meet, being this point. So now let's find this optimal point. We know that 1 minus alpha optimum lambda min has to be equal to alpha optimum lambda max minus 1. And so alpha optimum is equal to 2 divided by lambda min plus lambda max. This is true because we need that the absolute value of 1 minus alpha lambda min to be equal to the absolute value of 1 minus alpha lambda max. We can notice that 2 divided by lambda min plus lambda max is smaller than 2 divided by lambda max. So the optimal step size satisfies the bounds we have found previously for the gradient descent to converge. Condition number 3. We define the condition number of a positive definite matrix A as theta to be lambda max divided by lambda min. Let's write an upper bound on beta using the condition number of A as we found in the previous question. I encourage you to try to solve it yourself and then view the solution. So the solution is as follows. Beta is smaller than the maximum I over the absolute value of 1 minus alpha optimum lambda I, which is the maximum over the absolute value of 1 minus alpha optimum lambda max and 1 minus alpha optimum lambda min. And so what that equals to, it is 1 minus 2 divided by lambda min plus lambda max, as we have seen in the previous question, multiplied by lambda min, and that is equal to lambda max minus lambda min divided by lambda max plus lambda min. And so that is equal to theta minus 1 divided by theta plus 1. As to remind you, theta is lambda max divided by lambda min. So let's assume that the step size can be modified at any iteration of the gradient descent algorithm. Let's find the optimal step size at iteration k, and let's call it alpha star k. I encourage you to try to solve it yourself and then view the solution. So the solution is, the update step is xk plus 1 equal to xk plus alpha k dk dk being b minus qxk, as we have seen in the previous questions. This is the minus gradient of the given function. So the optimal step size is given by alpha k star being the argmin of f of xk plus 1. That is being the argmin of half xk plus alpha dk transpose qxk plus alpha dk minus b transpose xk plus alpha dk plus c, as this is the definition of the function f. And so derivative with respect to alpha, as we get, is dk transpose q xk plus alpha dk minus dk transpose b. So let's equate it to 0 and see what the alpha value is. And so we get that alpha multiplied by dk transpose q dk is equal to dk transpose dk. And so the optimal alpha at iteration k is dk transpose dk divided by dk transpose q dk.